So very good afternoon to everybody present here. In this class of bioinformatics and genetics, we discuss about the probabilistic modeling and inference. We discuss about the very simple sequence models. Then we discuss about the statistical mechanics. You would understand why you need a mechanics here. But of course, it has to do with some statistical as well as analytical part. So that is the reason we bring some mechanics concept in our bioinformatics and genetics. So this is especially for you, my dear students and young researchers. And you can reach me at dr.christoananth@gmail.com. So before beginning the session, let me thank God for giving me this golden opportunity to deliver this useful session to share my knowledge among my fellow national, international participants, students and young researchers. So today's class we discuss about the simplest sequence models, and then I will be explaining you with the help of a diagram about the two views of the four-sided DNA die. Okay, so that which is very much helpful to generate the DNA strings. Then we discuss about the negative log likelihood, and then we discuss about the model-based inferences. Then there is some Kolmogorov's axioms, and then we discuss about the over-aggressive quantification, about the quantitative network models, and then we discuss about the point estimators. So that's all about the mathematical part. And then we already discussed about entropy, maximum entropy, we discussed them. So in this particular class we discuss about the entropic distribution. Okay, and then we discuss about the second part of today's class, which is the multiple die model with the sequence data, and then we discuss about the statistical mechanics. So in the statistical mechanics we discuss about the Boltzmann-Gibbs distribution. Okay, so please go through the independent work, please complete them, and at regular intervals I will be giving you some short videos to discuss the knowledge in our topics. Right, so you imagine tossing a coin. It has both head as well as a tail. Okay, so maybe the same thing we would experience with the case of sequence model. So we will consider an alphabet A. It has two probabilities. Either head will occur or maybe tail can occur. So H you can term it for head, and T you can term it for tail. Okay, so similarly when you are dealing with the DNA sequences, so maybe with a more simple version you will be using some sequences, but in the complex part generally we will have maybe instead of 2 letters we will have 4 letters. Okay, remember in the first class, you remember I showed you a video, A, T, H, D sequences, A, T, H, D sequences. So the same thing we would experience with the case of complex sequences, and the possibility of observing longer strings as well. So here in the single die model we will have 4 letter alphabet. So this one A, C, G and T. Okay, so this is the model where we have the strings we will have obtained by the independent process of the same four-sided die. Okay, so maybe you will have maybe for this one G, T, C and A. Okay, A, C, G and T. Okay, so this one, these are the two views of the four-sided DNA. So 4 sides it has A, C, G and T. So this is the likelihood considerations that we will have with a long string. Let us consider a sequence of length n. Here actually D is said to be a set of O. So O is nothing but the sequence of x1, x2, x3 up to xn, where you take a general model xi which belongs to the total number of sequences which is A. So the model M will be having 4 parameters with A, C, G and T. So it is PA, PC, PG and PT. So you can tell that the sum of the probabilities is equal to 1. Okay, so maybe if you take in the case of maybe a coin, you will have head as well as tail. Okay, so what is the probability of head? It is equal to 1 by 2. Yes. What is the probability of tail? It is also 1 by 2. So if you add 1 by 2 and 1 by 2, you get 1. The total probability is equal to 1. Similarly for this 4 sides. Probability of A plus probability of C plus probability of G plus probability of T is equal to 1. So you can say probability of A is nothing but 1 by 4. Probability of C is 1 by 4. Probability of G is 1 by 4. And probability of T is 1 by 4. So if you add 1 by 4 plus 1 by 4 plus 1 by 4 plus 1 by 4 equal to 1. So this is the likelihood. So P of D by M is equal to pi of x belongs to A. So it is Px power nx, which is equal to probability of A power Na multiplied by probability of C power nc multiplied by probability of G power ng multiplied by probability of T power nt. So here nx is nothing but the number of times that the x appears in the sequence code. So this is the uniform prior distribution. Here we will have a L of the sequence summation x belongs to A, nx multiplied by log px minus lambda 1 minus summation x belongs to A px. So this is nothing but uniform prior distribution, where we would be having the parameter estimation problem would be considering of the ML parameters. So this is the Lagrangian operator. So L denotes the Lagrangian operator. So L is equal to minus summation x belongs to A, nx log px minus lambda 1 minus summation x belongs to A px. So this is where we have the negative log likelihood. So we will have minus negative log likelihood, and it is obtained with the case of the summation parameters. So generally you can have the derivation, okay, like dou L by dou Px to be equal to 0. So generally the probability, the probability Px would be equal to nx by lambda. Okay. So here the normalization constant, or maybe the normalization constraint, will give lambda is equal to the total number of sequences, which is n. So this is the probability of the likelihood. So Px star is equal to nx by n for all the x sequences like xi, x1, x2, x3 up to xn. It will be belonging to A, the total subset. Okay. So when you consider this limit n tends to infinity minus 1 by n, summation x belongs to A, nx multiplied by log nx divided by n equal to minus summation x belongs to A, px star log px star. Okay, so it is nothing but the entropy function h of p star. Okay, so this entropy you can consider to be the relative entropy. So generally it will be expressed as the set of the observed frequencies, like maybe px divided by n, or maybe if you take the total the sequences, it will be nx divided by n. Okay, so this is the observed frequencies nx divided by n. So the negative log likelihood comes from here, minus. So this is the thing with the case of observed frequency estimate. So whenever you have to calculate, for example, in this one, you are calculating the the observed frequency to be nx by n. So this is the estimate, observed frequency estimate. Px is equal to nx by n. Okay. Suppose let us take in the case we have a sequence of length 4. Okay, and for example we have like a, c, g and t. Suppose let us take in the case a does not appear at all. Okay, so maybe whether probability of a is equal to 0. Okay, so maybe we will have a confusion whether if a doesn't appear, so probability would be 0. So if in that case, generally we will go with the prior beliefs which do not favor the model parameters with value 0. So for this condition, maybe if this item doesn't appear, so maybe we can take the Dirichlet's condition. So this is the Dirichlet prior. Okay, so d alpha q of b. So here we will have the model based inferences where we would be considering this Dirichlet's prior. So we would be considering this probability of a sequence to be occurring at some non-uniformities. Okay, so for this case we would have a observational model. We would understand its limitations also. So within the observation model we will consider inferences. So From the inferences, we will tend to develop some consistent model configurations. So we can actually define these inferences from the observations that you try to make with the help of the observational model. So the probabilities you can calculate, the prior estimates you can benefit, and then you can calculate the observed frequency and the alpha factor. So this is the model based inferences. We will have observational space y and then model configuration space, which is theta, and the observational model can be given as y comma theta. Okay, so it is given as phi s of y comma theta. Okay, so this is the observational process. Okay, this is the observational space. Okay, and this one is the decision that you have to make. Whenever you have to make a decision, whenever you have to make a inference, generally you should have some observation. I can tell you with one particular example. Okay, for example, let us consider an exam where we try to write. Okay, so for the writing the exam, you need some space for writing. Similarly, you need some space in the answer paper. Okay, so whenever you write, generally, for example, one particular question is given. You read the question, then you make a decision. What decision you make? Okay, I studied this one day before this particular question. Okay, so you try to think about it. Okay, you make a decision. And what is the inference that you get? What are the subheadings in that question? What are the main points in that question? That is the inference. For this thing, you should have some observation. What is observation? Before one day, you have to study. Experience. Okay. So this entire thing, you call it to be the observational process. Okay. So the model-based inferences, we will have the quantification of the model with the case of the observed data. Same thing you can explain with the help of the the bioinformatics principles. So this is what we are going to do. So in the previous case, we had only from the observational space, it goes to the inferences and decisions, and similarly we go with the observations. Okay, the second case, after doing this one from the inference and decision, we are going back to the observational space. Okay, we are going to access this model configuration space as far as the observational model. So this model based inferences, you are going to come up with the informed decision. You are going to interact with the phenomenon. You are going to bridge the gap between the observed data and the latent system. Okay, so this one from the next diagram, from the previous diagram, from the inference and decision, it goes to the observational space, and the next one, it is going to interact, it is going to bridge the gap between the observed data and the latent system. So from this observational space, it goes here. So for this statistics based approaches, we would be introducing this frequentist approach. So frequentist methods we would have to measure in the case of the probability function. Okay, for example, as I told you in the previous diagram, we had like four phases. Okay, A, C, G and T. So we are going to find out the ratio of the rolls, right? So we are finding the rolling of one particular phase, maybe A or maybe C or maybe G or maybe T. So maybe what is the maximum probability it might occur. So we categorize the total number of rolls. Okay, total number of rolls, how many times you are going to roll this dice. Okay, what is the maximum time A occurs? What is the maximum number of times C occurs? What is the maximum number of times G occurs? What is the maximum number of times T occurs? So that you are going to categorize. So all the observers would encounter the same limiting frequencies. Like for example, everybody will get a chance to roll it. Okay, so the probabilities would be physical and it would be independent of the observer. So this is Kolmogorov's axioms. We will have the probability of A to be greater than or equal to 0, probability of S to be equal to 1, and for the intersection of the two sets A and B, so A intersection B is equal to phi. Similarly, if A intersection B equal to phi, then probability of A union B, which means A and then plus B, equal to probability of A plus probability of B. Okay, so this is Kolmogorov's axioms. So we would be analyzing the restriction of this resulting probability theory. It can be applied to the events which are repeated infinitely, or maybe at least hypothetically. Okay, so we would analyze the restriction with the case of the loopholes, that it provides a mathematical foundation for the inferences. Okay, so we can summarize: probability of A greater than or equal to 0, probability of S is equal to 1, and if A intersection B is equal to 5, then P of A union B is equal to P of A plus B of B. So we have like probability theory. We will have two types of probability. We will have the frequentist stats as well as Bayesian stats. Okay. So with the case of frequentist stats, we will have like p-value, and with the case of Bayesian stats, we will have the probability. So we can define the consistency with these models. So we will have like individual model configurations which are consistent with the observation, or maybe we can have similarly with the case of the right case with the case of probability theory. So where we tend to model the observational space. Okay, we will have the model configuration space. So now we come into over-aggressive quantification. So over-aggressive is all because of the the weakness of the binary configurations that we would be experiencing with the model configuration. So if it is very much inconsistent, or maybe it is not been able to make some decision, then comes over-aggressive quantification. So we will have like irrelevant features of a observation. Maybe we will tend to discard some important model configurations as well as true data also. So in order to compensate, we have to consider an approach which would be treating the inference as a decision making process. So for the decision making processes, we would be considering some binary quantifications. So for this case, we would categorize a decision making process. So here we will be explaining A of y bar. Okay, so that will be calibrating with a model based utility function u of a comma theta. Okay, so this is the model that I am talking about. With the case of point estimators, we will have theta cap, which is from y tends to theta and the small y tending to theta cap of y. Okay, so this is the natural utility function which will be complementing a point estimator. So u of y cross theta tending to r plus. Okay, so we would have both the parameters y comma theta to be belonging to minus theta cap of y minus theta the whole square. So this is nothing but the squared error. Okay, so for the model configuration, we would be computing the expected utility u bar of theta, which is equal to minus the differentiation dy pi s y of theta, and the squared error. Square error is nothing but theta cap of y minus theta the whole square. Okay. So the point estimators, once again, we would be calculating the expected utility to be u bar of theta is equal to minus integral dy by s y theta and multiplied by theta cap of y minus theta. So this is nothing but the squared error. Okay, right. So here we will be considering a single day model with the counts data. Okay, so we in the previous case we found out this one d bar m. So probability of d bar m is equal to p of nx bar px, which is equal to n factorial divided by pi, for which x, the sequences x1, x2, x3 up to xn belongs to the subset A. Okay, and then nx bar multiplied by pi. Pi means nothing but the total multiplication. Whenever we have summation, which means plus 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 plus. For pi means it is multiplication. Okay, so pi of x belongs to A, px power nx. So this is the Dirichlet's prior. We would be categorizing a Dirichlet's distribution. Okay, so with the d beta r of b with the beta factor, the normalization constant with the Dirichlet's distribution equal to n plus alpha, and the region of the relationship, we have rx equal to nx plus aqx divided by beta. Okay, so with this slash b divided by beta. Okay. So Stirling's approximation can be calculated as n factorial is equal to n divided by e power n into square root of 2 pi n. Okay, So from this we categorize the logarithmic function. Log of P of D bar P equal to C minus H is nothing but the entropy. H is entropy minus H of Nx divided by N comma Px. The entropical distribution can also be expressed as P of D bar P equal to exponential of H of Nx divided by N. The total thing divided by Z. Z is nothing but the total of the entropical functions. So for this case, we would be categorizing, using the max end principle, maximum entropy principle. So from this, we would be using this entropic prior. Okay. So in order to find the similarities in the sequences, in order to categorize the sequence to sequence model, we would be using the max entropy principle using this entropic prior. And this is the entropic prior, exponential of minus summation x px log px divided by z. So for any of the map estimate that we will be finding, we will be finding p multiplied by x is equal to nx by n. Okay, so that's px is equal to nx by n. Similar to the single die, we will have a multiple die model with the sequence data. So here we would be considering many sequences like k sequences, each of the n length. Okay, so with this case, the gap symbol we will have like a dash. It is considered as one of the symbols in the alphabet. So in the multiple die model, we will be considering k sequences, each of which have n independent dices. Okay, so each sequence is the result of flipping the n dice in the fixed order. Okay, so let us take in the case pi of x denotes the probability of producing the letter x with the die number I. Okay, and ni of x be the number of times the letter x appears in the position I. So because this die as well as the sequences are very much independent, so we would be finding the likelihood function for the case of any of the functions. Then we would have statistical mechanics. So it is nothing but one of the examples of the Bayesian reasoning. So for this, we would be using both the maximum entropy principle as well as the Bayesian concept, or nothing but the Bayes theorem. So the statistical mechanics is concerned with the macroscopic properties. So just like as you see in the diagram, there are many of the interacting units, microscopically interacting units. So if you see, there are several units over there. So there are some phase transition from one state to this state, from this state to this state, and so on. So we tend to use the statistical mechanics in computational biology and synthetic physics as well. So where we would try to evolve a number of graphical models used in the machine learning, and we tend to apply these statistical mechanical models in the biological macromolecules. From this, we find out the Boltzmann-Gibbs distribution. Here we will have some states. These are considered to be microscopic states, like S is equal to S1, S2 up to Sn. So that is given by the total subset S. So Ps is nothing but the probability of the state S, the initial state S, for that distribution P. So it is given by Ps. And similarly, we will be having a die model M of W with the parameters W equal to Ps. So this thing, we will have some microscopic states, but it will be acting as hidden variables in order to find the similarities between the sequences. So the statistical mechanics is not only about microscopic models, it's also about macroscopical models. So we tend to find out the D factor equal to E of F, the energy function, which is equal to summation S, summation over S, Ps multiplied by Fs. So for this case, we would considering the microscopic structure. Each of the sequence S would be of x1, x2, x3 up to xn. Xi, x1, x2 are nothing but the local variables, and xi is nothing but the binary spin variables. So this total state S is given by 2 multiplied by n. Okay, and F is given by the energy. So we will have Fs is equal to Fx1, Fx2 up to F of xn. Okay, so it is given by two components I and j. So weight factor of ij multiplied by x of I multiplied by x of j plus summation over I wi xi. So for the first thing it is I and j, second thing only I. Okay. So this interaction parameters can be local, and in the case of the spins it will be as a long range model in order to better analyze the similarities between the sequences. So for each of the thing we would be explaining with the help of the graphical model. Please complete the independent works, stochastic grammars and linguistic learning experience. So these are all associated with the neural networks. Please complete them and submit them in the Google Classroom.